Hello again. So this whole video is just some more example problems on integration by substitution because I understand that it's a really tricky process when you first learn it. So the more examples you see and the more you see to pick your U and those different patterns that pop up, the easier it's going to be for you to start picking up on those patterns on your own. So let's get started. So we have 4 more example problems here. So the first one we're going to do is something like cosine squared of x times the sine of x. So now something that's good to remember for trig functions is that their derivatives and antiderivatives work together a lot. So since we have a cosine squared of x, that doesn't pop up as a derivative of any trig functions. But if we pick our u to be cosine of x, we know that the derivative of cosine of x is just negative sine of x. So if we pick our u to be cosine, our du is just going to be negative sine of x dx, which means that we have this cosine taken care of here, so this is just going to leave us with a u squared. So now all we want to replace is that sine of x dx, which we can get by just multiplying both sides of our du equation by -1 to get positive sine of x dx. So now we can just rewrite this integral to simply be u squared times negative du, which we can pull the negative out front and just make this negative u squared du, which is going to give us negative u cubed over 3 plus c by just simply applying our power rule, and then plugging back in for our u is just going to give us negative 1/3 cosine cubed of x plus c. So it's as simple as that. So you might have been saying, well, how did you know to not pick the whole cosine squared? Well, if I had picked my u to be cosine squared of x, I would have had to use the chain rule when I took my du, and I would have gotten 2 cosine of x sine of x dx, which the sine of x dx part is good, and we could get rid of the 2 really easily, but I already took out both of my cosines and made them my u, so I wouldn't have an extra cosine around to replace this thing with over here. So that's how I knew not to do it. And you might have said, well, how did you know not to let your u just be the sine of x? Well, if I had picked my u to be the sine of x, my du would have been the cosine of x dx, which is almost exactly what we would have wanted, but I have a cosine squared of x. So I couldn't have gotten that by just multiplying both sides by the cosine of x because I would have been left with cosines still in my integral. So those were your 3 options. So if you just start playing around with it, you'll start to see how they work out. So now let's try something like the sine of 5x dx. So we know how to integrate something like the sine of x dx. So it's just the 5x part that's currently on the inside of the sine that's giving us any trouble. So why don't we let our u be the 5x? So whenever you're looking at an integral and you say, okay, I know how to do this, but this little part of the current problem I'm working on is what's throwing me off, try and let that be your u and see what happens, because it usually is whatever is causing the problem is going to be your u. So if we find our du, we just get 5 dx, which is almost exactly what we have left, so we just need to get rid of that extra 5. So just multiply both sides by 1/5 to get your dx. And now all we have to do is change this to being the sine of u times 1/5 du. So now that our whole integral is in terms of u, I can just pull that 1/5 out. We're going to get the sine of u du, which we know from all the integration that we've done before is just going to be 1/5, and then the antiderivative of sine is just negative cosine of u plus c. Now all we have to do is simplify our coefficients and then substitute back in for whatever u was. So u is 5x. So our final answer is just going to be negative 1/5 cosine of 5x plus c. So there you go. That problem was only 4 lines long, and it seemed like it was going to be a little bit more complicated from the get-go, which is why u substitution is such a great method. So 2 more examples. Okay, so let's get into how to do definite integrals with u substitution. Now there's 2 ways to do this. You can treat it like an indefinite integral and do your u sub, find your answer, and change your answer from u's back to x's, and then evaluate from 1 to 2. Or you can skip that middle step of switching back from u's to x's rather, and just keep your answer in terms of u's. And we're going to do that method so that you can get a taste of how that works. So since we know how to integrate the square root function, and we can notice that we have an x squared in here and an x out here, which is just 1 power less, we know that our u is probably going to be that x squared plus 5. And then if we take our du, we're going to get 2x dx, which we only want an x dx left over, so we're just going to get that 1/2 du is equal to x dx. So now I can rewrite my integral to be the integral of the square root of u times 1/2 du. But if I want to write that 1 and 2, I have to write this as x equaling 1 to x equaling 2. So in the next step, I want to get rid of those little x's on my integrand sign. So I'm going to pull this 1/2 out front, u to the 1/2 du. And now if I know that the bottom this is x equaling 1, so I want to know what that is in terms of u. So all I'm going to do is say, okay, well u is equal to x squared plus 5. So if I plug in 1 and do 1 squared plus 5, that gives me a u of 6. So I'm going to write a 6 here on the bottom. And I can do the same thing for the upper limit of integration. If I plug in 2 for x, I'm just going to get u is equal to 2 squared plus 5, which is equal to 4 plus 5, or 9. So instead, I'm just going to do the integral of 1/2 u to the 1/2 power from 6 to 9. So now if I integrate, I'm going to get 1/2 times u to the 3/2 over 3/2, all evaluated from 6 to 9, which is going to give me 1/2 times 2/3 u to the 3/2, evaluated from 6 to 9. If we simplify those coefficients, the 1/2 is going to cancel with the 2, so we're going to get 1/3 u to the 3/2, evaluated from 6 to 9. And now we're just going to use that first fundamental theorem of calculus to simplify this and get a numeric answer. So you always plug the top limit in first, so we're going to get 1/3 times 9 to the 3/2 minus 1/3, 6 raised to the 3/2, which is just going to be equal to 1/3 times, so we're going to do the square root of 9 and then cube it. So the square root of 9 is 3. 3 cubed is 27. Minus 1/3. So now, let's see. The square root of 6 is just the square root of 6. So the square root of 6 cubed is equal to the square root of 6 times the square root of 6 times the square root of 6. So we can multiply these first two together and get 6 times the square root of 6. So this is just going to be minus 1/3, 6 square root of 6 here in the end. Now if we just simplify, we're going to get 9 minus 2 square root of 6, which is our final answer. Now you could have done this by going all the way back up to this step right here and said, okay, I'm just going to plug back in for my u now. So you could have gotten that this was 1/3 times x squared plus 5 raised to the 3/2, and done the evaluation from 1 to 2 then, instead of from 6 to 9 if you kept it in terms of u. But that's an extra step, and mathematicians are notoriously lazy people, so why do the extra step if you don't have to? Just change your limits of integration over to what they equal in terms of u, and then just keep your whole integral in terms of u, and keep solving forward. You'll get the same answer either way. So let's do one more definite integral. So this is the integral from 1 to 5 of x over the square root of 2x minus 1. Okay, so you might be thinking, I have no idea what to do with this integral. But because we have matching powers of x, it means that we're probably going to have to do something like we did in the last video, where we make a u substitution and then have to solve our u for x so that we can rewrite the extra x's in our integral as a function of u. So why don't we let u equal to 2x minus 1? You almost always want to let u equal whatever is under a square root. So we're going to have that du is equal to 2 dx. So to solve for just the dx, we're going to get that 1/2 du is equal to dx. So we have this 2x minus 1 taken care of with our u. This dx can replace with 1/2 du. So it's just this x up top that's giving us any issue. So let's just solve for x from this equation right here. So if we solve for x, we're going to get u plus 1 is equal to 2x, or 1/2 of u plus 1 is equal to x. So that means I can rewrite this integral as the integral from x equaling 1 to x equaling 5. We'll switch over to u's in a second, of 1/2 u plus 1 over the square root of u, which we're just going to instantly write as a u to the 1/2 power, times 1/2 du. And now all we're going to do is simplify our coefficients and change over our limits of integration to terms of u, and then we're just going to simplify inside our integral, do our integration, substitute in with our first fundamental theorem of calculus, and we'll get our answer. So I'm going to pull this 1/2 out front and this 1/2 out front. So when I do that, I'm going to get 1/4 times the integral of u plus 1 over u to the 1/2 du. And now if I plug in 1 for x into this equation again, I'm going to get u is equal to 2 minus 1, which is equal to 1. And then if I plug in the top limit of integration of 5, I'm going to get u is equal to 10 minus 1, which is just 9. So instead we're going to do the definite integral from 1 to 9 of this function. So in order to integrate this, we first need to split up that function since we only have one term in the denominator. So this is really going to be u to the first over u to the 1/2 plus 1 over u to the 1/2 du. And now we can use our exponent rules to simplify that so that we can get something like u to a power, use our power rule of integration, and be good. So to simplify this first one here, u to the first over u to the 1/2, to make that just 1u, we just do the subtraction between the exponents. So 1 minus 1/2 is going to give us 1/2. And then for this one over here, all we want to do is bring that u up to the numerator, and we're going to do that with a negative exponent. So this is just going to be u to the negative 1/2 du. Now all we have left to do is integrate and substitute in. So we're going to get 1/4 times u to the 3/2 over 3/2 plus u to the 1/2, because negative 1/2 plus 1 is positive 1/2, over 1/2, all evaluated from 1 to 9, which is just going to be 1/4 times 2/3 u to the 3/2 plus 2 u to the 1/2, evaluated from 1 to 9. Now if I distribute my 1/4 through and simplify, 1/4 times 2/3 is going to give me 1/6 u to the 3/2 plus 1/2 then u to the 1/2. And now we're ready to plug in for 1 and 9. So if we plug in for 9 first, using our fundamental theorem, we're going to get 1/6 times 9 to the 3/2 plus 1/2, 9 to the 1/2, minus 1/6 of 1 to the 3/2 plus 1/2, 1 to the 1/2. And now all we have to do is simplify and find a final answer. So we're going to get 1/6 times the square root of 9 is 3. 3 cubed is 27. So we get 1/6 times 27 plus 9 to the 1/2 power is simply the square root of 9. So that's 3. So we're going to get 3 times 1/2, or 3/2, minus 1 to the 3/2 is 1. So we're going to get minus 1/6. And then the square root of 1 is just 1. So distributing that negative sign, we're going to get minus 1/2. So now all we have to do is simplify. So 1/6 times 27, I can cross cancel and make with a 3 and then make this a 2 and this a 9. So we're going to get 9/2 plus 3/2 minus 1/6 minus 1/2. 9/2 plus 3/2 is 12/2. Minus 1/2 is going to give us 11/2 minus 1/6. So our common denominator here is going to be a 6. So I'm going to get 33 over 6 minus 1 over 6, which is just 32 over 6, which everything there is divisible by 2. So 32 divided by 2 is going to give us 16 over 3, which is going to be our final answer. So I hope this extra video of example problems for use substitution helped you understand it a little bit more. But thank you so much for watching. Have a great rest of your day.